Hello, I am Raghav Gupta and I am going to present my project Human Profiling and Activity Recognition for Gator Patrol Robot. Gator Patrol is an autonomous robot which is designed for surveillance of a city. Work on the robot is divided into two vital parts. The first one is autonomous navigation of the robot and the second is threat recognition. This project aims to deal with the problem of human sensing and person detection in real-time scenarios for the implementation of human profiling and activity recognition. The solution is especially designed to work with single-board computers. The outline of this presentation is going to be a brief discussion about the approach, various algorithms that I have used, how these algorithms are implemented and executed, the results obtained under numerous scenarios using these different algorithms, followed by a conclusion of things, and finally how this project lays the foundation for future work related to this field and what all can be done to further improve upon the results. The approach targets at building a robot named Gator Patrol, which comprises majority of a common robot platform like motors, controller, connecting cables, power supply, etc., along with a powerful camera and an ARM-based processing unit. The idea is largely focused on identifying and implementing the existing technologies for human sensing and face detection in the Gator Patrol robot system using its powerful microprocessor and camera. Since OpenCV predefines many common descriptors for such purposes, thus it has been extensively used in this project. OpenCV libraries are also ported to the Odroid platform and linked with the robot operating system, which drives the fundamentals of the robot. This slide describes about the approach in relevant terms in a bit more detail. Human sensing and face detection can be described in two integral parts. The first one, which deals with feature identification, and the second, which deals with learning of these feature vectors. A feature is just a quantifiable property. Precise structures in an image like points, edges, and objects are individually or collectively known as features. Further, a common neighborhood operation or feature detection algorithm applied to an image may also result in a set of features. A feature vector is appropriately described by a set of numeric features. Classification is considered as an instance of supervised learning, that is, learning where a training set of correctly identified observations is available. Further, it can be defined as assigning a category to a new observation on the basis of pre-assigned categories of a training data set. Proper learning and training of the classifier helps in increasing the accuracy during the detection phase. Let's talk about the quality of the hardware being used for the realization of Gator Patrol. Odroid XU4 is a sufficiently powerful single-board computer to execute various complex tasks. Its specification consists of 2 GHz octa-core processor, 2 GB of RAM, 32 GB eMMC storage card, Mali graphical processing unit, and its dimensions are 82 by 58 by 22 millimeters. The Sony PS3i is a very popular camera used for various computer vision and image processing applications. It comes with USB 2.0 high-speed transfer connection and outputs an image of 640 into 480 resolution at 60 frames per second. Human sensing and face detection is realized using algorithms based on the combination of feature descriptors like HOG and HAR features and classifiers like cascade classifier and SVM. A HAR-like feature takes into account neighboring rectangular areas at a definite location in a detection frame, sums up the pixel intensities in each region and computes the variance between these sums. A simple hair-like feature for face detection is also shown in the figure. HOG, or histogram of oriented gradients, entails counting occurrences of gradient orientation in confined areas of an image, as can be seen in the figure. Cascading involves a combination of multiple classifiers, which helps in attaining better predictive performance than obtained by any of the constituent classifiers individually. As can be seen in the figure, this approach ensures that the data generated at the output of the former classifier in the cascaded network is provided to the later one as an additional information. Support vector machines are supervised learning models that analyze data and recognize patterns. As can be seen in the figure, they simultaneously minimize the imperial classification error and maximize the geometric margin. Hence, they are also known as maximum margin classifiers. For this project, two different sets of code bases are considered for evaluation purposes. The first code base is developed on C++ platform and implements cascaded classifier based on hair-like features, while the other is developed on Python and implements support vector machine based on the HOG feature descriptor. Both the code bases are integrated with OpenCV libraries. These code bases are executed on a high configuration laptop as well as Odroid XU4. The dataset considered for testing of the algorithm comprises of two random YouTube videos of sufficient length. The videos have been scaled down to decrease the computational complexity involved in processing a single frame. These videos depict a first-person view of the surroundings while the person is walking in the city. This representation is very similar to the output of the camera mounted on the Gator Patrol. The use of these videos provide an excellent example of the environment observed by a human in his day-to-day life, and thus allows the simulation to reach the realistic and practical aspects of a live environment. The slides here summarizes the result for the cascade classifier, which uses hair-like features. The detected objects are marked by white ellipses. The first figure depicts single and multiple humans detected in an image during real-time application. It also shows humans with posterior towards the camera being detected. The second figure shows a false positive case for the classifier. Multiple human figure being detected in an image is being manifested by the third figure. The fourth figure shows how frontal faces are successfully recognized by the classifier. This slide summarizes the result for the SVM, which uses HOG descriptor. The detected objects are marked by green rectangular boxes. In the first figure, multiple humans are detected in an image during real-time application. It also shows humans with posterior towards the camera being detected. The second figure shows a false positive case for the classifier. The third figure depicts multiple human figure being detected in an image. The fourth figure shows people with side poses being detected by the classifier as well. It is observed that the accuracy of the HOG far supersedes that of the hair feature descriptor, which is manifested in the figure where SVM with HOG is able to detect multiple persons in the same image, in which cascade classifier using hair features does not detect any due to partial occlusion and crowdedness. It is also observed that HOG SVM is computationally very expensive as compared to a combination of hair with cascade classifier, and thus a considerable lag is observed in its execution on Odroid XU4. Due to this, it cannot be implemented as such on Odroid XU4 or similar single board computers for real-time applications. Also, it is noted that both the approaches generate almost the similar number of false positives for a real-time environment. To conclude the results and observations, the most influential factors for the problem at hand and its solution are the computational efficiency of the algorithm and the resolution of the input video. The accuracy of the SVM plus HOG far supersedes that of the Cascade plus HAR feature descriptor, but this cannot be the only mediating factor while implementing human sensing algorithms on single board computers. Since single board computers are not as powerful as a machine powered by Intel processors, preferably i5 and i7, the computational expense of the algorithm plays an important role in deciding the framework to be used. For real-time applications, the resolution of the image and thereby the video plays a crucial role in deciding the time required to process a single frame. This in turn will decide the amount of lag induced while perceiving the action performed by a person in an observed environment. To overcome the shortcomings described above, some improvements have been proposed for future endeavors. This slide provides a brief summary of the same. Improving robustness of current algorithms. Optimize algorithms for Odroid XU4. Both of these can be achieved by using thread-based algorithm implementation for Odroid XU4. For illustration, different processes like image acquisition, image processing, and output analysis can be assigned to different threads. Executing the algorithm in this manner will prevent the addition of latency caused by its individual segments, thereby decreasing the lag significantly. Furthermore, ideas like detecting the direction of motion of a person with respect to the movement of the robot and identification of complex activities like a person trying to steal a car can be realized based on the work presented in this project. We will now take a look at the demos. The first demo shows the working of the Cascade classifier with HAR-like features. To run the code, one has to first compile it and then execute the main file. As previously described, white ellipses will signify the presence of the intended object of interest. As you can see, the classifier does not make a good start and misses a lot of people standing in a crowded manner. It can be seen here that the white ellipsis keeps on appearing at certain random places. These are the false positive cases for the analysis. This means that the classifier finds some kind of resemblance in the features obtained from the training data and the highlighted portion, which ideally it shouldn't. It should be noted that the detection of human figure in side poses is not handled by the classifier due to the lack of the training data. But on the other hand, detection of a person with his back towards the camera is quite easily achieved by the classifier. Multiple people being detected in this scenario can be easily observed. Environmental variations can critically affect the performance of an algorithm if not properly accounted for. For illustration, even during the daytime, the luminosity of a region can vary depending on the position of the sun. Owing to this, the algorithm is not able to efficiently detect these people walking in the shadow of the building. Although this lone gentleman is detected perfectly due to his clear visibility. The quality of the hardware used to capture the environment, in our case the camera, attributes directly to the quality of the results obtained. For illustrations, a camera may work exceptionally well to capture an area in daylight, but may induce immense noise when used at night under artificial yellow or white lights, which may cause problems for, for the algorithm used to detect person. Some more false positives can easily be seen here. It can be seen here that the activity being performed by an individual does not affect the detection process until they maintain an upright posture, and therefore both the running and walking men are correctly detected by the classifier. Identifying humans in a generic environment is a very complex task and requires a combination of integrate concepts of computer vision and statistical probabilistic theory. The cascade classifier using the hard-like features seems to perform decently well for the given real-time scenario. Next, we are going to observe the performance of the SVM, which is using HOG descriptors. In this video, green rectangular boxes will signify the presence of the intended object of interest. The very first thing that catches the eye is the high latency in the output video. This is because of the computationally expensive nature of the SVM classifier using HOG features. On the other hand, it should be noted that where the cascade classifier using the hard-like features completely failed to detect individuals in the crowded area, the SVM plus HOG worked exceptionally well. This is because of the robustness of this classifier. Similar to the previous demonstration, the occurrences of false positives can easily be seen here as well. Similarity to background is another major challenge faced during sensing the presence of a human. Even though many techniques have been employed for background segregation, the problem is still far from being resolved. The most challenging aspect of this problem can be explained by visualizing a person standing in front of an advertisement board or graffiti, which also comprises of more human figures. While a person can easily identify and segregate the advertisement from the interested entity, same may not be the case for a computer. The computer may either end up recognizing all the human-like figure present in such a frame or identify only the wrong person from the advertisement. The possibility of identifying only the correct entity is extremely trivial because it is very difficult for a computer to detect liveliness based on a simple capture of a frame. This problem can be dealt by analyzing motion of the interested entity in more than one frames, given that a change transpires in the position or posture of the person. Thank you.